Hey there, I'm Hussein, and welcome to the second episode of the Grasshopper course from scratch. So, last session we learned how to create our very first geometries, input data into Grasshopper, and work with components. Today, it's time to dive into one of the most crucial parts, basic geometries and transformations. In this video, we're going to explore the foundational components of geometry, lines, curves, and those awesome 2D and 3D shapes. And guess what? We're also getting into transformations. We're going to learn how to move, rotate, scale, mirror, and orient those geometries. These things are like the foundation of parametric design, and they make our forms and models in Grasshopper super dynamic and controllable. I'm going to try to show you step by step how those components you saw in Rhino are used in Grasshopper. If you're ready, let's dive into the world of movement and geometry behavior. Let's get into part 2. In the first episode of Grasshopper from Zero, we got familiar with the basic concepts of parametric design and saw how we can build geometry from scratch that's both controllable and responsive. We started by exploring the Grasshopper environment and how it connects to Rhino. Then, we learned how to use components and data flow to create points, lines, circles, and boxes, and control them with numeric parameters. We also covered how to bring existing Rhino geometry into Grasshopper, manage different types of data, and understand the difference between algorithmic design and manual modeling. Finally, we explained the concept of bake, turning parametric geometry into real Rhino models so that we're ready to dive into transformations and shape modifications in the upcoming episodes. In the previous episode, we talked about construct point. Now, let's look at a few more basic tools to deepen our understanding of geometry in Grasshopper. First up, we have line SDL. SDL stands for start, direction, and length. This component creates a line that starts at a specific point, follows a direction vector, and extends to a defined length. In simple terms, it's like saying, draw a line from this point in this direction for this distance. Because of this, line SDL is extremely useful for parametric tasks, like creating rows of lines, series of elements, radial structures, or any form that depends on vectors. All right, let's see how line SDL actually works. First, we have the start point. This is simply where your line begins. You can plug in a point you created with construct point, or use a point from a curve or a grid. Next is the direction. This tells the line which way to go. Remember, it has to be a vector, not just a point. For example, if you want the line along the x-axis, you use unit x. If you want it to go perpendicular to a surface, use surface normal. Finally, there's the length. This controls how long your line will be. You can usually hook up a slider here to change it dynamically. One tip, if your vector isn't normalized, the line might not behave as expected, so make sure your direction vector is properly set. And that's it. The output is a straight line that starts at your point, goes in the direction you specified, and extends for the length you set. Simple, flexible, and really powerful for creating patterns, grids, or vector-based forms in Grasshopper. Next, let's talk about Polyline. The Polyline component creates a continuous, connected series of straight lines. It's basically a multi-segment path, connecting a list of points in order. In simple terms, every point you plug in becomes a vertex, and Grasshopper draws straight lines between all of them. This path can either be open or closed. If you close it, the last point connects back to the first, forming a complete shape. How does the Polyline component work? The first input is V, or vertices. This is the list of points your polyline will pass through. The order of these points defines the final shape, so make sure they're arranged correctly. If the points are out of sequence, the polyline can twist or create unexpected turns. The second input is C, or close, which is optional. If you set it to true, the polyline closes into a loop. If it's false, it stays open. In many cases, you don't even need to use this input. You can always close the curve later using tools like close curve or boundary surface. And finally, the output, a clean polyline that connects all your vertices and forms the line or shape you intended. Now let's move on to Interpolate curve. This component creates a smooth NURBS curve that passes exactly through your points. Unlike a polyline, it doesn't draw straight segments, it produces a continuous flowing curve that interpolates all the points. In simple terms, give it your points, and it will draw a smooth, precise curve through them all. It's perfect for organic shapes, soft lines, controlled paths, and architectural forms. How does the Interpolate curve component work? Here are the inputs. First, V or vertices or points. These are the points the curve must pass through. The order is important. If the sequence is wrong, the curve can twist or behave unpredictably. Next is D, or degree, which is usually set to 3. A higher degree makes the curve smoother, but also harder to control. Then we have P, or periodic, an optional input. When it's set to true, the curve becomes a clean, smooth, closed loop. This is useful for rings, closed profiles, or organic shapes. And finally, the output, a smooth, accurate NURBS curve that you can use to build surfaces, sweeps, or any next step in your modeling workflow. Now let's talk about ellipse. This component creates a smooth oval shape defined by a major axis and a minor axis. Unlike a circle, which just needs a center and a radius, ellipse uses a plane to position itself in 3D space. That means its orientation and rotation completely depend on the plane you provide. In simple terms, you give it a plane, set the major axis length, set the minor axis length, and the ellipse is ready. How does the ellipse component work? The first input is the plane. This defines both the center point of the ellipse and its orientation in 3D space. Then you have radius 1, which sets the distance from the center to the end of the major axis, and radius 2, which sets the distance to the end of the minor axis. Just keep in mind, these are radii, not full diameters. For the outputs, the main result is a smooth, closed ellipse curve. You also get the final plane, which can be helpful for further modeling, and 2 additional outputs, the major axis curve and the minor axis curve, which you can use for reference or for additional operations in your workflow. Now let's move on to rectangle. This component creates a rectangle on a specified plane. The size of the rectangle is controlled by 2 values, the length and the width. In simple terms, you give it a plane, a length and a width, and it generates the rectangle for you. Rectangle is a fundamental tool for creating grids, boxes, profiles, floors, details, and parametric structures. The first input is the plane, which determines where and in what orientation the rectangle will be placed. For example, if you want a rectangle on the ground, use the XY plane. The second input is X size, which sets one dimension of the rectangle, usually the length. The third input is Y size, which sets the other dimension, usually the width. If X and Y are equal, the output will be a square. The main output is a closed rectangle curve, which can be a rectangle or a square. You also get the plane on which the rectangle is constructed, useful for further modeling or reference. Next, let's talk about offset. This component moves a curve by a specified distance, either outward or inward. It's basically the same as the offset curve command in Rhino, but in Grasshopper, it's fully parametric. In simple terms, you give it a curve and a distance, and it creates a new curve at that distance from the original. Offset is very useful for thickening shapes, creating walls, generating spacing, producing geometric patterns, or making new sections. The first input is curve, which is the curve you want to offset. Distance sets how far the new curve will be from the original. Positive values move the curve outward, and negative values move it inward. Plane determines the direction of the offset. For flat curves, you can use the XY plane. And for 3D curves, you might use a perpendicular frame. Finally, corner style controls how corners are handled, with options like sharp, round, or square. The default is usually sharp. The main output is the new offset curve. You also get the actual distance applied, which is helpful for checking and verifying your results. Next, let's talk about fillet. This component connects two curves or segments and creates an arc between them, softening the corner. In simple terms, instead of a sharp corner between two lines or curves, fillet makes a smooth curved transition. This is very useful in architectural forms, paths, profiles, or anywhere you need rounded corners. The first input is the curves, which includes the two lines or curves that you want to fillet. The second input is the radius, which defines the radius of the fillet. A larger value creates a wider, smoother corner, while a smaller value keeps the corner sharper, closer to the original angle. The main output is the combined curve with the smooth fillet corner. Additionally, you get the fillet arc as a separate output, which can be used for further operations. Next, let's talk about sphere. This component creates a 3D sphere. Spheres are widely used in architecture, parametric design, organic modeling, and geometric forms. In simple terms, you provide a center and a radius, and a perfect sphere is created. Spheres can also serve as a base for more complex surfaces, lofts, sweeps, or organic forms. The first input is plane, which sets the center and orientation of the sphere. The center of the plane becomes the center of the sphere, and the z direction of the plane defines the vertical axis. Radius sets the distance from the center to the surface of the sphere, which can be controlled with a slider or a fixed number. Optionally, you can use diameter instead of radius, but only one of radius or diameter should be used at a time. The main output is the 3D sphere itself. You also get the plane used as input, which can be useful for further operations like alignment or referencing. Now let's look at cone. This component creates a 3D cone, which consists of a circular base and a tip. Cones are very useful in architecture, organic forms, and parametric modeling, especially for creating sloped volumes or conical roofs. In simple terms, you give it a center, a base radius, and a height, and a complete cone is created. The first input is plane, which sets the center and orientation of the cone. The center of the plane becomes the center of the base, and the z direction points toward the tip. Radius defines the radius of the base circle. Height is the distance from the center of the base to the tip of the cone. Optionally, you can use diameter instead of radius, but only one of radius or diameter should be used at a time. Outputs. The main output is the 3D cone. You also get the input plane for further operations like alignment. Now let's talk about cylinder. This component creates a 3D cylinder consisting of a circular base and a height. Cylinders are widely used in architecture, parametric modeling, columns, and volumetric forms. In simple terms, you provide a center, a base radius, and a height, and a complete cylinder is generated. The first input is plane, which sets the center and orientation of the cylinder. The center of the plane becomes the center of the base, and the z direction defines the cylinder's vertical axis. Radius sets the radius of the base circle, and height determines the distance from the base to the top. Optionally, You can use diameter instead of radius, but only one of radius or diameter should be used at a time. The main output is the 3D cylinder. You also get the input plane, which can be used for further operations like alignment or referencing. Additionally, the component outputs the base circle and the top circle as curves if you need them for further modeling. Next, let's look at cap. This component closes an open surface or volume. In simple terms, if you have an open volume or surface, cap can seal the ends or holes to create a closed solid. This is essential for preparing geometry for Boolean operations, 3D printing, or creating fully enclosed forms. Inputs. The input is brep, or surface, which is the geometry you want to close. This can be an open extrude, loft, sweep, or any open surface. Outputs. The output is a closed brep. The cap component usually detects automatically which ends of the geometry are open and closes them. Finally, let's talk about extrude curve. This component takes a 2D curve and extends it in a specified direction, turning it into a surface or solid. In simple terms, you give it a curve and a direction, and it produces a volume or surface. This is one of the most fundamental ways to create parametric 3D forms from lines or curve. The first input is curve, which is the curve or line you want to extrude. It can be open or closed. If the curve is closed, the output can be a closed brep. Vector sets the direction of extrusion. This can be the Z vector or any custom vector in space. For a fixed height, you can use a vector like. Solid is optional and determines whether the output should be a solid or just a surface. The output is a brep or surface that has been extruded. Now, let's quickly cover vector basics. Unit X, unit Y, and unit Z are 3 unit vectors, which means their length is always 1. Each one points along one of the main axes. Unit X points horizontally, unit Y points along the vertical direction of the XY plane, and unit Z points perpendicular to the XY plane. These unit vectors are the most fundamental tools for moving geometry, extruding, and performing all kinds of transformations in Grasshopper. They make it easy and precise to define directions for any operation. Transformations. Let's start with move. This component is used to move any type of geometry or curve in a specified direction by a set distance. In simple terms, you give it an object and a vector, and the object moves in that direction by the given distance. Move is the foundation for all parametric movement and object repetition, and it works seamlessly with unit vectors and other vectors. The first input is geometry, which is the object or curve you want to move. Translation is the vector that defines the direction and distance of the movement. This can be a unit vector, like unit X, Y, or Z, or any custom vector, even a combination of multiple vectors. The output is the moved geometry. Next, let's cover rotate. This component rotates an object or curve around a specified point in a 2D plane, like XY, XZ, or YZ. In simple terms, you give it a center point and an angle, and the object rotates within that plane. Rotate is very useful for simple 2D rotations on a surface, like turning a rectangle or curve on the XY plane. The first input is geometry, which is the object or curve you want to rotate. Angle sets the rotation angle in radians, which you can control easily with a slider. Center defines the point around which the object rotates. Plane is optional and specifies the plane of rotation. If not provided, XY plane is used by default. Outputs. The output is the rotated geometry. Now let's look at rotate 3D. This works like rotate, but in 3D space and around any axis you choose. In simple terms, you give it an axis and an angle, and the object rotates around that axis. This is essential for complex 3D rotations like spinning a cylinder or surface in space. Inputs. Geometry is the object or curve to rotate. Angle sets the rotation in radians. Axis defines the rotation axis, which can be a line between 2 points or any line in space. Outputs. The output is the geometry rotated around the specified axis. Next, let's talk about scale. This component resizes an object or curve uniformly around a reference point, called the base point. In simple terms, you give it a base point and a scale factor, and the object grows or shrinks around that point. Scale is very useful for resizing forms without changing their original geometry. Geometry is the object or curve to resize. Center is the reference point around which the scaling happens. Factor sets the scale amount. A number greater than 1 makes the object bigger, and a number less than 1 makes it smaller. The output is the scaled geometry. Now let's look at scale NU. This component scales an object or curve differently along each axis. In simple terms, you give it a separate factor for x, y, and z, and the object stretches or shrinks independently along each direction. This is useful for modifying shapes or stretching forms in one or more directions. Inputs. Geometry is the object or curve to scale. Center is the reference point for scaling. Factor is a vector defining scale amounts for each axis. Fx for x, Fy for y, and Fz for z. Outputs. The output is the geometry scaled non-uniformly. Now let's look at mirror. This component reflects an object or curve across a specified line or plane. In simple terms, you give it an object and an axis or plane, and it creates a mirrored version of the object. Mirror is very useful for creating symmetry, double-sided patterns, and parametric designs. Inputs. Geometry is the object or curve you want to reflect. Axis is the line or axis of reflection around which the object is mirrored. Optionally, you can use a plane instead of a line for the reflection. The output is the mirrored geometry. The original object remains unchanged, and mirror generates a new reflected copy. Okay, so in this part, we learned how to work with basic geometries in Grasshopper, and we took this really big step into the world of transformations. We saw how we can create lines, polylines, soft curves, ellipses, rectangles, and even 3D shapes like spheres, cones, and cylinders in a totally parametric way. Okay, so the most important thing here, we figured out that these basic geometries are actually the foundation. They're the core of transformations and all those more complex forms we're going to get into later. If you've got a good grasp on this part, the whole parametric design journey is going to be way easier for you. If this video was helpful, make sure to hit that like button and subscribe to the channel so you don't miss out on the next episodes of the course. And as always, if you've got any questions or suggestions, just drop them down in the comments below. I'll totally get back to you. Thanks for sticking with me till the end. Until next time, see you later.